Okay, let's get started. It is my great pleasure to introduce today's being seminar speaker, Professor Babbs. We are honored to have Professor Babbs as the first seminar speaker of this whole semester. This brief introduction, I don't want to take any of his time. Dr. Babbs received his bachelor's degree from Yale and then received his medical degree from Baylor College of Medicine and then received PhD at Purdue. So he's a Boilermaker. He's a founding member of Purdue Biomedical Engineering Center in 1974. Actually, his research spanned across broad areas from electrical, ventricular defibrillation, hyperthermia, from cancer research, and recently I moved here Google Scholar, and there's some studies about EEG data detection of stroke, and some ultrasound focusing. And actually, you're doing some astrophysics, as well, like multi-body astrophysics studies. So he covers everything from physics, biology, medicine, biomedical engineering. In fact, Dr. Babbs needs no introduction. He is our leading memoir of London School of Biomedical Engineering. Personally, I wanted to record one of these seminars and lectures to preserve part of our BME 50s event. Without further ado, please join me welcoming Professor Babbs.
All right, is the sound working? Can you hear me all right?
Yeah.
Does that sound good? All right. Thank you. And thank you for the kind introduction, Professor Kim. Without further ado, my mission today is to tell you the story of the first 25 years of biomedical engineering at Purdue. And the reason for this is because Purdue is celebrating 50 years of biomedical engineering at Purdue, beginning about now. All right. And my job is to do the first 25 years, and then I'll let other people, perhaps like George Wadicka, do the next 25. Okay. So my mission today then is to talk about some cool scientific ideas. This is a talk for graduate students and undergraduate students. It is not a talk, this is the part of it I said I wouldn't say, but it's not a talk about money, it's not a talk about awards, it's not a talk about marketing. It's a talk about science and ideas, and it's about interesting people, some of whom are here, including, most importantly, the graduate students that made it happen. So let me begin by the story of how biomedical engineering got started at Purdue. And interestingly, Purdue was a real leader in biomedical engineering movement. This chart shows you the number of BME programs in the country as a function of calendar date. And we're starting back here in about 1973. So the first 3 years, I was a peon. And okay, so this is lore that got directly from Dr. Geddes. And according to his very words, it started out because back in about 1973, there was a council of deans. Those words, a council of deans, which corresponds to the deans of all engineering now, because we didn't have heads then, we had deans. And they got the idea, presciently, that there were opportunities to explore the application of engineering principles to healthcare. And this was a new idea. And they decided, we want Purdue to get on board with this. And they had some discussion. And they decided that there were going to be some ground rules. The first one is that when it comes to biomedical engineering, it should be money coming into Purdue, right? into their departments. It should not be a new school like we have now. It should not be a new school that took the dean's money away from other existing departments. No, we're going to have an interdisciplinary research center of excellence. All right? And so what they did was decided we're going to establish this in name, and they determined the first director of the Biomedical Engineering Center, and that was Paul Stanley. And Paul Stanley was a professor of air transportation, according to history. And he was the director of Purdue's first Biomedical Engineering Center. Now, there's another character that comes into play at this juncture, and that is Bill Hillenbrand. And Bill Hillenbrand was the chairman of Hillenbrand Industries in Batesville, Indiana. And it was one of the largest Indiana-based corporations at the time, said to be competing for the richest man in Indiana with Bill Cook. Let's see whether that is really true. And Bill Hillenbrand said that I have made a fortune selling 2 products that nobody wants to use. Caskets and hospital beds. And so we had 2 major companies, Batesville Casket, and you may have even seen those on I-65 going up and down with the pine trees, you know, and that's, all right. Batesville Casket and Hillrom Company, and Hillrom Company was the hospital bed company. Now, like all classical entrepreneurs, and that's an overstatement, in America, and one of the ways to success, if you want to get rich, okay, here's how to do it. What you do is you make excellent products and services and sell them to rich people. All right, I mean, that's how you do it. And Bill Hillenbrand was about the same. And so he had the world's best caskets, and they were really proud of them, and they were really expensive. But if you wanted to go out in style, you got yourself a Batesville casket. And he also wanted to have the world's best hospital beds. Back in those days, he decided that he was going to modernize the hospital bed by making the hospital bed motorized. He was going to put a motor on it that raised the head of the bed when you pushed a button and lowered it when you pushed another button. Now, you probably think that that's normal, right? But that was an innovation in 1970s, and Hillrom started it. And they started making these wonderful motorized hospital beds. But there was a problem. The nurses hated it. And so he decided that he would go right to the source. And by the way, this became a Hillrom tradition, a serious, that they talked to the nurses. They talked to the users, and they got feedback from the real world. And that became a tradition at Hillrom. And the nurses said, well, what's wrong with our wonderful hospital beds? And they said, well, when I go up to them, sometimes I get a shock. Woo! Okay, and sometimes I don't, but a lot of times I get a shock, and it's terrible. And Bill Hillenbrand somehow got word of this biomedical engineering at Purdue. He contacted Paul Stanley and said, can you help? And he gave him the problem, and he gave him access to the information. And Paul Stanley very quickly figured out what the problem was. And that is the electric motors that raised and lowered the beds were connected directly to the steel frame of the bed. All right. And the electric were not grounded, okay, which meant that there was a current path from the motor to the bed, to the nurse, to the ground, okay? So Paul Stanley figured that out, and he decided that the best solution would be to take a piece of wood, screw the motor into the wood, screw the wood into the bed so that there's an insulated boundary between the motor and the bed. It worked great. The problem was solved, and Bill Hillenbrand was absolutely thrilled. And he said, this is fantastic. The world needs more of this wonderful biomedical engineering. And so he provided a gift to Purdue to rocket launch biomedical engineering at Purdue, $2 million. That was back in the days when $1 million was a lot of money. And so the dean was absolutely delighted and decided now we can recruit the world's best biomedical engineer and have a true center of excellence at Purdue. All right. Now here's another character that comes into the early stories, and that's Bob Hanneman. Bob Hanneman, who was a pediatrician in town who took care of my kids from time to time, also was a professor of chemical engineering at Purdue. And Bob Hanneman had already achieved a certain notoriety because he was studying bilirubin concentration in premature babies. And the problem is that bilirubin is a product of the breakdown of hemoglobin in blood, and premature babies haven't quite yet developed, in many cases, the enzymes to metabolize it. And so the bilirubin builds up in the blood and is toxic to the brain and can cause long-term and serious brain damage. And Bob Hanneman was the one who appreciated this, being a chemical engineer, and he also appreciated that you might be able to detect this if you had the right light. Now, does this sound familiar with cell phones and stuff like that? If you had, if you had the right light and the right frequency, what would happen is it's be easy to detect this and take countermeasures. And furthermore, he went on to discover Billy lights. That is to say that by using the right frequency, it would actually stimulate the bilirubin to the double bonds in bilirubin, at least one of them, to absorb extra energy and convert to a more water-soluble compound that could be gotten rid of. And so not only could he do diagnosis of hyperbilirubinemia, but also treatment. So he was the biggest, baddest thing that Purdue had in biomedical engineering. There was some other politics on the side, which I'm going to skip. All right. And so the dean went to Bob Hanneman and he said, well, we want to recruit the world's best biomedical engineer for Purdue so we can become famous for this and bring in lots of money as long as it doesn't take away from the dean's budget for our program. Right. And Bob said, I'm not I'm a chemical engineer. I don't know anything about, what do you mean? I just happen to, I happen to also be a pediatrician. I'm interested in this, but I don't know. It says, well, you're the only one we've got, so you got to find somebody. So Bob Hanneman was able to go down to the IU School of Medicine library and talk to his friend who was a librarian. And they said, I want to find all the books you have in the IU School of Medicine library about biomedical engineering. Could you please search that? And she did. And she came back with one book. And the book was written by a couple of guys in Houston, Texas, L.A. Geddes, Leslie Geddes, and Ellie Lee Baker, who were in the Department of Physiology at Baylor College of Medicine. And so the dean sent an expedition to Baylor College of Medicine, all the way to Houston, Texas, BCM. At that time, I was a lowly medical student at Baylor and didn't know what was going on. But later on, when I did a senior research project with Dr. Geddes, my laboratory was right there. It actually had windows. I could see the sunrise. In Geddesonian tradition, I get up early and I actually watched the sunrise out of my windows. So this is where Dr. Geddes was. Here he is, along with a student near the physiograph, the device that he invented to modernize graphic recording of physiologic events in the 20th century. And you could look out my window and you could see the School of Nursing, which is out of view. And there is Linnell Geddes, who became Dr. Geddes' wife, and she became a good friend. I never beat Linnell into the lab early, all right? One time, I would get there at 5 a.m. and she would always be there, all right? So one time I decided that I was gonna be the first. So I tried to get there at 4 a.m. Dang, Linnell was still there making coffee. And she, of course, she went down there, became the head, if I didn't say this before, the head of the nursing school at Purdue University, and a great friend. Okay. Now, why would, okay. So what happened is that Geddes, I must have missed. All right, I put in a new slide, but it's not here. And that is that Geddes got his start doing monitoring of astronauts for the Mercury program, in which he was able to monitor respiration and impedance with one set of electrodes, which is now considered cool again. And people are using it for smartwatch technology. All right. So he was the best biomedical engineer in the country. And they made him an offer. And Geddes said, well, you know what? I'm really happy here. He had just gotten, more funding from NASA, and he had a couple of others, and he had graduate students, and he had a lot of collaborations with people around the surgery department and so on. And so he says, well, maybe I won't go. I don't really want to go, but I'll tell you what I'll do. I'll write down a list of 10 names of people in the United States that would be good for the biomedical engineering position at Purdue. And they sent them back. A year later, the same search committee came back to Baylor after the Hillenbrand gift. And they said, we've spoken to all 10 and we still want you. Then they made him an offer he couldn't refuse. And so what happened is that we moved from Houston all the way to Indiana. And by that time, I was one of the ones who helped load the van. In those days at Baylor, it happened to be that the culture was that the principal investigator who bought equipment on a grant owned the equipment. So they actually had a checklist. It was 4 pages, single space, checklist with the grant numbers and the dates of all the equipment that he had bought as a PI. And we loaded that onto a van, and the dean approved everything so that we could start out with a working laboratory at Purdue. And so we got in the van and drove all the way to Indiana. Now, in those days, remember that Dr. Geddes was an ME, Masters of Engineering in Electrical Engineering, with a PhD in physiology. So one of the things that Geddes was most interested in was the interaction of electric current with the body. And the coolest thing at the time, it's because high power electronics were cool in those days. Okay, it wasn't like today where everything is micro and nano. Okay, it's wholly high power electronics were cool. I think that might even be a hydrogen thyratron. I'm not sure. Okay, and so the obvious application, which is only a decade or so earlier had been invented by Paul Zoll, founder of Zoll Medical, all right? A cardiologist from Harvard Medical School. And he had shown that it's possible to abolish the lethal rhythm disturbance, ventricular fibrillation, the most common cause of sudden cardiac death, by passing a high intensity, high current large electric field through the heart, bang, to stop all the abnormal rhythms and allow the natural pacemaker to resume. And you've heard of defibrillation, right? I'm focusing on things that technologies that you have know about or maybe have even experienced in your own healthcare that were started, if you're getting the theme of this, that were began here at Purdue. And a lot of people don't know. Many people don't know. Okay. But at those times, he was already starting to investigate defibrillation. Okay. And the problem is that when the abnormal rhythms start going around and around and around, a complex three-dimensional structure, such as the heart with two ventricles, then they can take multiple paths. And in each circuit, they can take a slightly different path. And then the next time, they can take a slightly different path. And so the fibrillating heart is classically described as by surgeons who had to open the chest immediately and then start squeezing in order just to save the person. They said it felt like a writhing bag of worms. The heart was like a bag of, and it was contracting, it was beating, but all in totally disconnected ways. But what can happen with an electric shock, if it's big enough, strong enough, and covers a wide enough area, is it can stop all of the impulses at once, the cells spontaneously recover in synchrony, and the heart may beat again. And that is the concept of electrical ventricular defibrillation. And so Geddes' first mission when he came to Purdue, being a high-power electrical engineer, when high power was cool, was say, well, let's optimize defibrillation. And I remember that he said, he would say, optimization by chance is unlikely. And so it must be that we could figure out a shock strength, a shock duration, and a waveform, either smooth, damped sine wave, or rectangular, or what they call trapezoidal waveform. Nobody knew what the best waveform was. Nobody knew what the best shock strength was. And he said, surely we can optimize this using principles of high power electrical engineering. And so when he came to Purdue, Geddes built the world's largest defibrillator in order to study this and control the waveforms and the power precisely. Here are the other three founders. This is Tak Tacker right here. This is Joe Borland. This is Leslie Geddes. This big machine that they're looking at right here with all these capacitors was the world's largest defibrillator ever built, and its name was Joule, Joule, after the unit of energy. And I realized to my delight that the world's second largest defibrillator is actually also pictured here, and that's in the background, and that is about the size of a refrigerator, and the name of that defibrillator was Big White. By the way, there's also a Little White, which still, I believe, exists in this building in the basement, and Bill Schoenlein is still here? No, I think it is. You can go find it. It was modified to do transcranial electrical stimulation with coils, and there's all kinds of fun stuff about that. All right, so they decided they were going to optimize defibrillation. And when I came into the picture, I was a graduate student in pharmacology. That's a Freudian slip. In pharmacology, technically at Purdue, the study of drugs. My professor was G.K.W. Yim in the School of Pharmacy. And one of the things we thought about is applying some drug-related concepts to defibrillation. And Geddes thought this was a great idea. He thought this was a great idea because he talked about the electrical dose concept, that the success depends on how much, not only which waveform, which corresponds to like which drug or which isomer, in a category of drugs, but also what the dose is. And nobody really knew. So we were the first folks to actually quantify this, because we had those experimental defibrillators that allowed you to go way into overdose. So in anesthetized animals we had at the time, we could look at the percent successful defibrillation, and then the percent that caused microscopic damage to the heart from an electric shock. And we could even calculate in a few animals the percent of that were actually killed outright by one shock. And in pharmacology, there's a classical concept called the therapeutic index, which is either the ratio of the lethal dose to the effective dose, which would be the ratio of and they talk about the LD50, which is the lethal dose that will kill 50%. And here it is here. And here is the dose that will treat or abolish fibrillation in 50%. So we could actually quantify this, and you can see it's not that far apart, but nobody knew how to measure shock strength. There were the peak current people, Geddes was in that camp. There were the energy people, the other people in that camp. So we did both, and we established it. This experiment will probably never be done again. And interesting, I just noticed that just last week they're downloading it in Seattle. Somebody is going back and revisiting there, and they're doing it in Singapore and in China. It's unbelievable that some of this work is being revisited. So in addition to the action of electric current on the heart, naturally, being a physiologist, Geddes would also think about, well, what are the other vital organs? Well, how about respiration? And so we had a study with Bill Voorhees, who started exploring what Geddes called electroventilation. And that is using electric current to stimulate respiration or breathing rather than stimulate the heart. Okay, and the good news is because of all that work on the basic science with the waveforms, we realized that the strength duration curve for stimulating the heart was much different from the strength duration curve for stimulating nerve endings that innervated skeletal muscle, specifically the nerve endings that go into the diaphragm. Okay, by over an order of magnitude, which means it's possible to give a shock that will stimulate respiration without causing a heartbeat. So to realize that there's a huge safety margin between the strength duration curve for motor nerves and the strength duration curve for cardiac muscle cells, it was possible to do this electroventilation process. And Geddes investigated, again here using an anesthetized dog, that there were places on the chest where you could stimulate inspiration. There were places on the chest stimulate expiration, and there were also places on the chest that caused paradoxical breathing, which means those are the P's, and that means simultaneously stimulating muscles for inspiration and expiration, which kind of creates a logjam. But this was considered, maybe this would work in anesthesia. Maybe this would work in emergency medicine. Maybe, all you modernists, it would work in drug overdose. It could work in the opioid overdose epidemic. That's another one, so you could work on that. Maybe there's a way you could just have a respiratory pacemaker that would keep people alive. Geddes did this back in the 1980s. Another thing that you might have heard of that is very closely held secret, you could say, is that esophageal ultrasonic scanning was invented at Purdue. And I personally held the world's first esophageal scanner in my hands. It was about, and I think it's still on display somewhere at Cook. Okay, still it's like, okay, it's about that long. It's a brass tube, at least 3/4 of an inch, maybe a whole inch in diameter. And the idea that Geddes had was very simple. And that was that if you look at the anatomy of the chest, the esophagus runs right behind the heart. Okay, what's the problem with ultrasonic imaging of the heart in general? The ribs and the lungs. The ribs reflect ultrasound, the lungs reflect, scatter ultrasound, and there's only a few little windows on the chest where you can get, like in the cardiac notch of the left lung, where you can actually get a decent view of the heart from the chest. So it's hit or miss, especially in people with advanced pulmonary disease and big hyperexpanded chests and flat diaphragms, someone like me. All right? I never smoked after age 13. Okay. And so we got the idea that we could get a great view of the heart from the esophagus. And David Hughes was the graduate student who built and tested the first esophageal scanner. And Neil Fearnot was the graduate student who actually did the whole PhD thesis with this and was also my office mate for some time. And the idea was we took this probe and put it down the esophagus like sword swallowing. And at the end of the probe was a rotating esophageal ultrasound transducer. And they had a way of syncing the position of the turning transducer with three-dimensional space, and in order to produce images of the heart, which look like this. And this is the world's first esophageal scan. And the study was done in a very, very large anesthetized German Shepherd dog that came from the animal shelter and would otherwise have been euthanized. And Dr. Tacker's comment was, no dog is too big for this study, because it was a big hunk. And the whole idea was to do this with a human-sized heart in order to get these images. So there is the world's first ultrasonics done at Japan, done at Purdue. Now, at the same time, there was a group in Japan, and most people think it was a Japanese invention because they actually went further and had continued funding and developed it into a device. But it actually started here at Purdue, and one of these days we can resurrect that if somebody wants to make an exhibit. Now, another thing that I know that you've all heard about and probably experienced is pulse oximetry. You've probably all gone to the doctor and had a clip on your hand. And the pulse oximeter was actually invented at Purdue by Mary Lee Evans, a graduate student in biomedical engineering. The concept of the pulse oximeter is to have a laser that emits a light, either in a reflected mode or transmission mode. There are two ways you can do it. The laser includes light in the absorption spectrum of hemoglobin, and then have a photodetector that picks up that light. And what Mary Lee Evans noted, being a student of Geddes who does graphic recording, she had a DC coupled original raw data record. And she realized that what happened, the signal that she got back had a big baseline. Okay, lots of contamination, but there was a pulsatile signal on top. All right, so there's a big baseline, and maybe 10% of the signal was pulsating. And she recognized that that waveform of that pulse was the same as the waveform of arterial pressure. A concept which now people all over the world are studying because of smartwatches. More on that later. Smartwatches. As a way of detecting the pulse. And there is Geddes holding Mary Lee Evans' first prototype of a pulse oximeter. Now, what was cool is that in the early days, Mary Lee Evans was doing actual experiments in the lab, And what she would do in order to save time was that she would take the laser and the photodetector and she would super glue them to her fingernails. And then there was wires that came out that she could attach to her apparatus and make measurements. So that would eliminate it. For the early studies, that was how she optimized the system. And on breaks, Mary Lee Evans would walk around the lab with wires coming out of her fingers. Okay, and after a few days, we just realized that was normal. So we had a student working around with wires coming out of their fingers. It didn't bother us. I thought that was kind of funny. All right. Now, let me go on to another thing, which, and that is that Geddes was also interested in blood pressure. And this includes work from Maynard Ramsey, who was one of his first students way back in Houston. That was in the Houston era. Maynard Ramsey became MD, PhD, and founder of a medical device company that made these things. The Dynamap, right? Dynamap was Maynard's company. And also Pat Young. Pat Young was a graduate student at Purdue who worked on optimizing the signal and interpretation of the signal from oscillometric blood pressure. Now, let me tell you a little bit about that. Let me see if I have my slide on that. Yes, I do. Okay. So if you put a blood pressure cuff around the arm, and instead of listening for the Korotkov sounds, which is the way you usually do with the stethoscope, instead you have a little transducer built in there, which Geddes just would, you go to the lab and he'd put some makeup on there and he'd do it. Okay, you didn't have to write a grant, you didn't have to stay in your office and yell at the grad students. He actually did it himself. And he would make this, and he would therefore be able to record the oscillations in cuff pressure. All right? And the oscillations in cuff pressure, and this is a famous illustration from his book, in which he shows oscillations in cuff pressure as the cuff is blown up above systolic. You have to start above systolic. We were consulting for a startup company here, like during the pandemic or slightly before, and there's groups that are doing this with smartwatches, and they start to the wrong end and screws up the data, and they have venous congestion. But anyhow, you start up above systolic, just like a regular clinical blood pressure, and then gradually let the pressure out of the cuff. And what happens is when the pressure in the artery is greater than the pressure of the cuff, the artery opens, whoop, like that. And then it closes. And that produces the Korotkov sounds if you're using the auscultatory method with a stethoscope, which is shown up in this top channel of the graphic record. These is a record of the Korotkov sounds. But also it produces cuff pressure oscillations. Cuff pressure oscillations. And so what they do is he records this and finds a systolic and a diastolic point, and that's by identifying that point where the cuff pressure oscillations increase to a certain threshold. That's the systolic endpoint. The diastolic endpoint is where the cuff pressure oscillations go out. Disappear, see that? And that was Pat Young's thesis. And what I did a little bit later was you have a physics-based model that actually would model the entire envelope and find the ratio of systolic and diastolic pressure that caused the least squares best fit the entire envelope. Now, here's something that it's a real secret. And there's a reason for that. The first smartwatch was developed at Purdue University. And the first smartwatch was done in what we call the Army Project. This started in 1981 after Ronald Reagan was elected president. And in those days, there was a great deal of fear among academics because Ronald Reagan's objective was to decrease funding for the NIH and increase funding for the military. And so Geddes, who knew that the first rule is to meet the payroll and keep the soldiers on board, all right, had an emergency meeting in the basement of the Potter Building. And that emergency meeting said, gentlemen, what are we going to do about Ronald Reagan? And he therefore proposed, we're going to have to start doing research for the military if we're going to keep the shop open in this environment. I realized to my horror and amazement as I was preparing for this, that Geddes did that for my benefit because I was the pacifist in the group. I was against the war in Vietnam. And so he was terribly afraid that, and so he staged this whole thing. It was like the Knights of the Round Table. I mean, you should see the chairs. They had carving on them, It was a rare book library. So what are you going to do about Ronald Reagan? We got to go after the military. So, okay. So he decided to do that and went out to, we went out to Natick, Massachusetts, and to Fort Detrick. And we talked to the Army generals in charge of essentially biomedical engineering, if not by that name. And this is, you can get this report now online. It has been declassified. And we did a final report to solve this problem that the Army had. And that was, how are we going to tell if a wounded soldier is alive in a full chemical defense suit and what they call the modern integrated battlefield, chemical, biological, and conventional weapons? And the problem is that if you do this, imagine sending a medic out. What they were terribly worried about is, first of all, the medic would be risking their lives, and maybe the person's already dead. Okay, because you really do have to kind of, I always use people for props. You really have to, if you're going to get a pulse, right? If you're going to get a pulse, then you have to take off the chemical defense suit. And how's the medic going to do that? Well, they didn't want them risking their lives to detect vital signs in a person who is already dead. And they also they didn't want to have the medic disrobe, because that would cause contamination. And this was their huge worry. All right. And so we came out with what is the first smartwatch, really. And this is a illustration from that final report, which actually comes from the original proposal. And it shows that we were going to explore sensors that the soldier would wear and wristbands like this. The final design, though, and because I worked on this for 2 years, the final design was a single watch. And it was a single watch that would sense the pulse using impedance and possibly even respiration using the impedance, the variations in the waveform. Okay, but it wasn't in the final report. And I remember reading this now, and I went to get it. And I said, why don't we put the final design? I said, no, that's the way the Army does things. That's for security. We do not want any record of our final design. We just want to send the product for testing and let the Army decide. So I couldn't find an illustration of the final design, but it was the first smartwatch. And it was tested by Jim Jones and Kirk Foster on the Purdue golf course. And what they did is they actually had these smartwatches that had radio capability, all right? And they had a central station and a mini computer, and these guys would go and hide behind some of the hills at the Purdue golf course, and they would, and other people would simulate being wounded soldiers and see if they could pick up the signal, and they eventually optimized this to the point where it would work, and we sent it off to the Army for testing. Now, along with runs of patient monitoring, I want to highlight Umesh Patel, my personal student, Umesh Patel later became president of Cook Biotech and a very successful parent, by the way, at West Lafayette. His kids did great. And this was the first computer-based automated telephone. And this is now getting downloads from Singapore and from Nigeria. Okay, and the idea, as well as Australia, and the idea was that we thought there would be a way to use modern technology to monitor patients with congestive heart failure at home. And Umesh made the first working system. And we actually had some interesting license agreements. I won't get into all that, but ultimately this technology was bought and sold and turned into the company called Telehealth, which is based in Hawaii and has subsidiaries here in Lafayette, Indiana, and you can get telehealth services in Lafayette, Indiana to monitor patients at home with simple equipment, including things like a smartwatch. Although what we did with heart failure, we talked to real doctors and real patients. And the two things they wanted to know to determine if a patient was getting worsening heart failure were symptoms and body weight. Body weight reflecting retention of edema fluid in patients with right-sided failure. Those were the things that they wanted to know. So we actually just send the patients at home with, and we tested this with real people with a scale. And we had these robocalls. Now you're probably getting them from politicians and so on. You're smart. You had robocalls, and what happens is that they would answer, they would report on their symptoms, they'd get on the scale and tell what the weight was. And those two data points were the key to tracking the progression of heart failure according to an actual algorithm, which we developed, and even it had a GUI. It had a user interface. And the thing that would tell the problem is if the symptoms were getting worse and the body weight was increasing, that was a sign that that patient was drifting into heart failure and they needed to get to clinical care before they went into acute pulmonary edema. And that, in principle, saves huge amounts of money and lives and trouble because detecting it early. And Umesh was the first right here at Purdue. All right, now what about you? What about the next generation of biomedical engineers? I'll let you look at that for a little bit. Hint, it comes from Children's Hospital in Queensland. Okay. Well, I suggest that it might be that you can take advantage of some of these ideas from the 20th century and perhaps using modern technology, create new and better versions here in the 21st century. And I want to put just a couple of examples of things that are still, you might consider, unfinished business of Purdue biomedical engineering. All right, one of these things is using heat therapy for cancer. Okay. And the idea is if you take a radio frequency generator, in this case it's microwaves, but you can also use radio frequency, and you put it through a coil, it is possible to actually apply thermal energy to a tumor. And because of the great collaboration and influence of one of my other mentors, who's David P. DeWitt, a mechanical engineering professor at Purdue, who wrote the book on heat transfer. And David P. DeWitt got me into the bioheat equation. And what we realized is that tumors generally have much poorer blood flow than the surrounding normal tissue. And they also have abnormal blood vessels without smooth muscle in their walls, which means that they do not respond to hormones and they do not respond to drugs. So the idea is that if the normal tissue responds to a drug that relaxes smooth muscle in an artery, increases blood flow, what happens is that the tissue blood flow after, and we used hydralazine as a classical direct-acting vasodilator, that what happens is the blood flow in the normal tissue goes way up, and there's even a vascular steal phenomenon in which the blood flow in the tumor goes down. And that improves, are you ready for this? The therapeutic index of cancer therapy. What's wrong with modern cancer therapy? The chemotherapy, the therapeutic index sucks, right? You have to have toxicity for normal tissue in order to kill the tumor. Well, this is, in theory, a great way to go. And this technology is still up for grabs, because if you can just eliminate the resistance of the normal tissues, which is variable because of the blood, because of the smooth muscle, responds to drugs, then the cooling blood flow goes up to the normal tissue and the tumor heats up. All right? Now, maybe all you people are interested in MR imaging out here and blood flow. Maybe in the 21st century, we could use MR imaging to determine which tumors have low blood flow to begin with, and how the normal tissues respond to drugs in a way that would make cancer doctors comfortable with giving cardiovascular doctors drugs to their patients, which they're a little bit afraid to do. Okay, because they could see you could see with your own eyes which tumors have less blood flow and more, and which normal tissues have greater blood flow, and then you could titrate the dose for that patient in a way that is compatible with modern clinical practice. Here's another, Phil Krause. Okay. Phil Krause invented this as a master's student. He's now a still active cardiologist in town with a little more limited practice though. And he found a way of getting inspiration-triggered oxygen delivery at home. And the idea was he simply invented a little, and we did this, he was my student, and he put in a little pressure sensor, which is shown on the side here, to an oxygen delivery system. And what happened was that when the patient took in a breath using the nasal prongs, the pressure sensor would detect that, and it would trigger a burst of oxygen. Think about it. With a normal oxygen delivery system, the oxygen is flowing all the time. When the patient inhales, the oxygen goes into the lungs. When the patient exhales, the oxygen just goes into, it's wasted. And so we could get more than a twofold increase in oxygen utilization efficiency with this system. And this has not yet been fully developed in America. And when I talked to the directors of the what is now Medicare, back in those days, this will save us, $500 million a year. This is great. Well, why didn't you develop it? Well, I'm here to tell you that you could carry this forward. All right, now don't worry about the mafia. The problem is that we got hate mail from the mafia, or at least Chicago lawyers that were impersonating the mafia. And we're very told that one of the things that the mafia did as a quasi-legitimate business was sell oxygen. And they didn't want anybody decreasing their sales by 50%, right? Okay, so we got this hate mail, and we were told by personal envoys, don't worry. Now that's probably just a Chicago lawyer's trick. So don't worry about that. You can do it now in the 21st century. And imagine the savings in 2025. All right, so my message to you is that you have a legacy, a great intellectual tradition. You as graduate students have the ability to make an impact. That's how science is really done. That's how we did it in the 20th century, and you can do it in the 21st century. So thank you very much. I did almost finish on time.
Can I have 1 or 2 minutes to have a couple of questions from students? Any questions? Go ahead.
What happened with the electrical stimulation diaphragm? Like what happened with that one?
Oh, what happened with the questions? What happened with the electrical stimulation of the diaphragm? That's a good question. It's still possible. It can still be done. One of the problems was that there are some people, including Joe Borland himself, one of the other founders, who are very sensitive to electrical stimulation. And so in a few people, they can sense the electrodes, especially if you don't put them on right and they're not coupled right and they're the wrong size and the wrong place, and they go out. And so since there were a small number of people who are ultra sensitive, it would never really make it, into practice because basically people will get sued for shocking. Most of the time, the electroventilation studies that we did and the applications that we talked about were in anesthetized patients. And in that case, like the drug overdose scenario, it worked great because they don't feel any shock. And as long as it doesn't stimulate the heart and cause arrhythmias, works fine. If you put the electrodes in the right place. What? You want more?
Okay, then let's thank Dr.
I'll be outside.
We're talking to take advantage of this. Thank you.